We will start our test 3 material with a special type of function which is more or less pretty similar to the linear and the quadratic function, except this time the power of the x in the function might not be necessarily 1 or 2. It can be any integer power. And we will call them polynomial function. So the first thing I will do, I will describe what will be a general form of a polynomial function. So polynomial function is a function of the form. So if I may write the function notation first. So y, the output, equal to fx equal to an x to the power n plus a n minus 1 x to the power n minus 1 plus dot 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 a 1x. So I say a 1x plus a naught. So where all these constants, so the constants an minus 1, a1, a0 are real numbers. We are going to only work with real polynomials. But we want to ensure that an is not equal to 0. N is an integer, and rather I should say a non-negative integer. So it can be 0, but it cannot be negative numbers. In this situation, the term an x to the power n, so basically the term with the highest degree for x, or the highest power for x, is called the leading term. And it will be interesting for us to know the leading term because it is going to help us understand the end behavior of the graph of a polynomial function. In particular, an is called the leading coefficient, and n is called the degree of the polynomial. So I said that these are functions that look like a straight line or a parabola and even more. So we'll talk about 3 special type of polynomial function before we dig in deep to understand polynomial function. So example 1 is y equal to fx, say equal to 5. So 5 is just a constant. Now this is going to be a polynomial function. So we said that this is a polynomial function of degree 0. Polynomial function of degree 0. And remember why this is so, because you can write it as 5 times x to the power 0. And you know that this is the constant function. The graph of this function is the horizontal straight line that passes through the point 0, 5. So the y coordinate on this line is always 5 units. So any constant function is a polynomial function. Second example is of course our second type of function that we have learned, and that is y equal to fx equal to mx plus b, where m is not equal to 0. And these are your general linear functions. Is also a polynomial function. So if you think about it, then the degree of x in these things are 1. So these are degree 1 polynomials. And likewise, we know that we can expect, if m is not equal to 0, of course, we can expect 2 different types of straight lines. Both of them are going to be slant lines. One is going up, rising up from left to right. And in this situation, we say that the slope n is greater than 0, and the other one will be slant line, that is falling down right to left, left to right. And in this situation, the slope is less than 0. But these are indeed polynomial functions. The other function we have learned is also polynomial function. So y equal to fx equal to, you can say the general format, ax squared plus bx plus c. We know that this is going to be a parabola depending on whether a is positive or negative. So pictures might look like this, and the vertex of course depends on the constants a, b, c. So this is a polynomial function if a is greater than 0. We can also expect a polynomial function of degree 2 where the graph looks something around the line of this, which is opening down, and this is being with the leading coefficient of a being less than 0. So these are polynomial functions of degree 2. So polynomial of degree 2. So what we will do now, we will talk about the domain of the polynomial function. So as you can imagine, in the previous 3 cases, it will be true for any polynomial function that the domain is always negative infinity to infinity. Whereas finding the range of the polynomial function is not as simple as finding the range of a linear function or a quadratic function. It varies very much on finding the relative maximums, relative minimums, if there is any. And so we will somehow learn how to talk about the range of the polynomial function, but at this point, with the maturity that we have, it is almost impossible for us to talk about the ranges of polynomial function. For some special polynomials, of course, I will show you how to find that range. What else? We talked about understanding the analytic equation of a polynomial function and identify the nature of the graph of the polynomial function. And that heavily depends on the degree of the polynomial and the leading coefficient of the polynomial. So there are 4 different situations as long as the degree and the leading coefficients are concerned. So I'm going to do a little table for ourselves. I will say the 2 possibilities for the degree of the polynomial functions is going to be either odd or even. And the 2 possibilities for the leading coefficient of a polynomial function, it is also twofold. And we will say these are either positive or negative. So let's see how we build up this table. If you know that the degree of the polynomial function is odd and the leading coefficient is positive, that's what we're going to answer first. If the degree of the polynomial function is positive, the odd, and the leading coefficient is positive, then we say the left end of the polynomial function goes down, and there are intermediate things happening in between, and the right end of the polynomial function is going up. One easier way to remember this pattern, remember what I said. I said degree is odd and leading coefficient is positive. You can always think of the simple equation y equal to x. The degree is 1, leading coefficient is also 1. So degree is odd and leading coefficient is positive. So that matches our situation. And if you think of the graph of this polynomial function, then it is the straight line that passes through the origin and rises up as we go left to right on the x-axis. So we repeat the same pattern on any polynomial function with odd degree and positive leading coefficient. Whereas if the degree of the polynomial function is even and the leading coefficient is positive, both of the ends of the polynomial function is going to go up. So again, how do I remember this situation? We'll think about the polynomial function with even degree. So easiest one is x squared, and I want to make the leading coefficient positive, so take that as 1. And this is our parent function y equal to x squared, And we remember this is a parabola that opens up. And if you look at the two ends of the graph, they're both going up. And that's how I remember. And as I said, I actually am not talking about what is happening intermediately. So this is what we do not know. We are just talking about the end behavior, the long run behavior. So as I said, we can call it the end behavior of a polynomial function. What happens to the graph, or the long run behavior. And so since I say that this is the long run behavior, we want to elaborate on this term a little bit. So this basically talks about what happens when the values of x increase without any bounds. So as we go far right on the x-axis and we go far left on the x-axis, what is the nature of the graph? So in order to understand that, we can say as x goes to infinity, instead of writing all of that as x is going far right, I say x arrow infinity, and I read it as x goes to infinity, the y values go to infinity. In fact, let me erase and give myself a little more room to complete this long run behavior. And so as we have talked about, there is one other end that we can talk about, and that is as x goes to far left, which is negative infinity. Y this time goes to negative infinity because the left end is falling down as well. Similarly, you can think about what happens in the situation when the degree of the polynomial function is even. Well, see, if x goes to far right or x goes to infinity, y goes to infinity as well. If x goes to negative infinity, y still goes to infinity as the left end goes up. So this is what is happening when we have positive leading coefficient, odd degree, and even degree. Well, how about the situation is a little changed now, and we are going to talk about odd degree, even degree polynomials with leading coefficient being negative. And probably you are already imagining what I'm going to do. I'm going to still play with straight lines. I'm just going to make and straight line and quadratic functions of parabola, but make the leading coefficient negative. So let's think about it. So start with y equal to x, so degree is 1, but make the leading coefficient a negative 1. So this is leading coefficient negative and degree odd. And remember, this is the straight line with negative slope, so the line will pass through the origin, but instead of rising up, it is going to fall down as you move on the x-axis from left to right. So, to sum it up, we say any polynomial function with odd degree but negative leading coefficient, left end goes up, right end falls down. So how do I write it in long run behavior? Remember, as x is going to infinity, the right end of the graph is falling down, so y must go to negative infinity. Whereas as x is going to negative infinity, so it's going to far left, then the y values are going up, so it goes to positive infinity. What if I have the degree of the polynomial function even? So similar situation, start with y equal to x squared. You need negative leading coefficient. Remember, a being less than 0, I have the situation where the graph is going to open downwards. So both left and right end for this situation will go down. And these are the precisely 4 different situations for end behavior for any polynomial function. So if I want to write it down in terms of long run behavior, I say as x is going to far right or x goes to infinity, y values are going towards negative infinity. If x is going to far left or negative infinity, y values are still going to negative infinity. So that's precisely what we are going to use when we will say the word long run behavior. The other thing that I want to talk about is the concept of zeros or x-intercept, and what does those things mean for our polynomial function and its graph. So remember, I talked about in different contexts when you solve the equation of a polynomial function for the value of 0, you're basically finding zeros or you're finding the solutions. or you are finding the x-intercepts, they are precisely the same information carrying thing. Or depending on the situation, we will call them roots as well. So precisely we're doing the exact same thing. So a polynomial function will have exactly as many roots or zeros or solutions as their degree is. So we'll say number of solutions. I'm going to be hesitant, a little hesitant to call it x-intercept at this point. So I'll precisely use the word the number of solutions. You can call it roots or zeros, but not x-intercept. Do not use x-intercept. So not x-intercepts for a polynomial function is equal to the degree of the polynomial function. Remember, in a quadratic function, we get two solutions all the time. But we also have a situation where we get complex conjugates as the solutions of the quadratic equations. And we have been talking about this thing since the last test period, that in those situations where you have complex solutions, you do not have real x-intercepts. So that's the same thing that we're going to consider for a polynomial function. If the solutions are complex numbers, they're not going to contribute in the number of x-intercepts, but you can call them solutions or zeros or roots. All right? Now, there are a couple more things that are associated with the graph of the polynomial function as well as with the concept of the degree of the polynomial function and hence the number of solutions. So we'll say the number of points where the polynomial function is changing its nature from increasing to decreasing or decreasing to increasing. So it's basically if you are doing this, which is from increasing to decreasing or from decreasing to increasing, those are called turning points. So this one, the first example is increasing to decreasing, and this point where it is exactly happening, it's a point of local maximum, and it is also called a turning point. And the other situation is when we are changing from decreasing to increasing, which is our second picture. The point of a local minimum or relative minimum is also called a turning point. So what we will now say is that the number of turning points of a polynomial function, how many times we are expecting this thing to happen, is at most, so to the most number of times if you count them, so at most degree of the polynomial function minus 1. And again, you can just think of the quadratic function as an example to understand polynomial function. Think about in a parabola how many times you are changing the nature from increasing to decreasing or decreasing to increasing. Exactly once, and that is happening at the vertex. Degree of the quadratic function is 2, so the number of turning points being 1, 1 is 2 minus 1, and hence I will remember this nature of the polynomial function, which says the number of turning points in a polynomial function is at most degree of the polynomial function minus 1. Also, the x-intercepts is going to give us a little more information. So we'll say if the degree of the x-intercept, which I'm going to call by a new name, and I will use the word multiplicity. So if the multiplicity of the x-intercept, it's the point where the graph is crossing or touching the x-axis, is even. What do I mean by that? If the corresponding solution to the polynomial function of this x-intercept is there for even number of times. For example, in a parabola, if you think about the parabola fx equal to x squared, the solution is 0, but it is present there 2 times, so that's even multiplicity. So if the multiplicity of the x-intercept is even, then the graph will not cross the x-axis. Then the graph touches the x-axis and bounces back. At that intercept, it will touch and will bounce back. Whereas if the multiplicity is odd, that means a particular solution giving you that x-intercept is there for odd number of times. It could be 1, 3, 5. So if the multiplicity of the x-intercept is odd, then the graph will definitely cross the x-axis. Then the graph crosses the x-axis. And finally, we talk about the graph of the polynomial function in general, of a polynomial function, is continuous. So there is no breaking in the graph of the polynomial function and is smooth. So if I give you a bunch of different graphs and ask you to find out which one of these are polynomial functions, you're looking for the smoothness of the graph and or the continuity of the graph. So what do I mean by smooth? I say that is there is no breaking in the graph, that's the continuity portion. And the smoothness says there is no sharp bending. In the graph is continuity where there is no breaking and there is no sharp bending. Remember the turning points? If I have sharp bending at the turning points, then these are not polynomial functions. So that is precisely what I wanted you to know about the nature of the graphs of a polynomial function. And we're going to go to the lecture note now and start working on this concept. So as usual, we have the formal definition of a polynomial function. It says that if n be a non-negative integer and an minus 1, a2, a1, a0 are real numbers with an not equal to 0, then the function defined by fx equal to an x to the power n plus an minus 1 x to the power n minus 1 plus dot 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 plus a2x squared plus a1x plus a naught is called a polynomial function of degree n, where the number an, the coefficient of the variable to the highest power, is called the leading coefficient. Determine whether the following functions are polynomial functions. If it is, then identify the degree. So the first one, it is a polynomial function and the degree is the highest power. So I say that yes, it is a polynomial function and the degree of this polynomial function is 4. Fx equal to x squared plus 3 over x squared. So first I want you to write it as x squared plus 3 over x squared, then distribute the division. So you get x squared over x squared plus 3 over x squared, which is 1 plus 3 times x to the power negative 2. Now see, in this one, it looks pretty close to become a polynomial function, except the power is a negative number, which we cannot have. So that is not a polynomial function. And because it is not a polynomial, we are not going to try to find the degree of the polynomial. How about given the graphs? So polynomial functions of degree 2 or higher have graphs that are smooth and continuous. So if I look at the first graph, I see that this is pretty continuous and the turning points here and here, they're pretty smooth as well. So I'm going to say that yes, I don't have to know what function I'm looking at. The graph tells me that it could be the graph of a polynomial function. So yes. Let's say the second one, you have the smoothness maintained. All the turning points are smoother. But there is a discontinuity in the graph at this point, at this x value. So because of the existence of this discontinuity in the graph, we will say that this is no longer a polynomial function. So this is not a polynomial. So just to give you one more example where I'm going to lack the smoothness, think about the function absolute value of x. That's the easiest function that I can think of. So this is y equal to fx equal to absolute value of x. The turning point is a sharp end. A sharp bend has happened there. So it is not a polynomial. It is continuous, but it is not a polynomial because of the sharp bend. And in fact, we know that this is a piecewise defined function where the breaking point is at 0. So this following paragraph is about the end behavior, and I'm going to skip this and go to our problems because we already talked about the end behavior. Polynomial functions and their graphs use the leading term coefficient test to determine the function's end behavior. So see, the leading term is the coefficient of the term containing the highest power x term. So leading term is all of it, 7x to the power 5. Whereas the leading coefficient, what I need, that is the coefficient 7, whereas the degree is 5. So what I have, remember we check the odd and evenness of the degree. So degree is 5, which is clearly odd, and the leading coefficient is positive. This is 7, so clearly a positive number. So what do I understand from that? That if I do the long run behavior, then the left end of the function will go down. We do not know what's happening in between, but the right end is going to go up. So we say left end goes down, right end goes up. What else? You can also say as the left end is going towards far right, or I say x goes to infinity, y is going to infinity, but as x is going to negative infinity, y is going to negative infinity. Fairly simple. So the zeros of the polynomial function, if f is a polynomial function, then the values of x for which fx is equal to 0 are called the zeros of f. And we know that they are also called roots or solutions of the polynomial function. Each real root of the polynomial equation appears as an x-intercept of the graph of the polynomial function. So the most important statement here is whenever the root is real, then I get to say that they are x-intercept, otherwise they are not. Multiplicity of the x-intercept, we have talked about it, so we are going to kind of use this idea and talk about the examples. What is the smallest degree of the polynomial which could have the following graph? So what I do, I'm going to find how many zeros we have. So I see that there are 4 zeros. So the smallest degree, it could be more than 4, but the smallest degree should be 4. Because remember, there could be zeros that are not necessarily x-intercept, but at least you have 4 x-intercept, so the smallest possible degree should be 4. What else you could have done? You could have counted the number of turning points. So this is one of the turning points, that's one of them, this is one of them. So when I got that information, the number of turning points remember this is going to be determined by the degree of the polynomial minus 1, and this is 3. So number of turning points is 3. So smallest degree again, because I say at most, so smallest degree is n plus 1, so that should be 4. Remember, number of turning points is n minus 1. So if you know the number of turning points is n minus 1, then the degree n is turning points plus 1. So that's why I added the 1 and I got 4. So in either way, I would say that the smallest possible degree of this polynomial is 4. So for the following two examples, we're going to find the zeros of these polynomials. We're going to use the multiplicity of the leftmost zero and the multiplicity of the rightmost zero to talk about whether the graph touches x-axis. First one is pretty simple. In order to find the zero, you just think about the equation, and it is the multiplication, the zero multiplication rule. So either x plus 3 is equal to 0, which means x is equal to negative 3 is one of your solutions. So you will say the zeros are negative 3, comma. The other one is x minus 7 to the power 2 equal to 0, which implies x minus 7 is equal to 0, which implies x equal to 7. So the zeros are negative 3 and 7. Negative 3 is the leftmost zero, so I will say this is negative 3. And the multiplicity is 1, because the 0 is exactly once in the factors. And that is odd. We are wondering whether the multiplicity is odd or even. So it is odd, so at this x-intercept, the graph crosses the x-axis. The rightmost zero in this problem is 7, but the multiplicity is 2. How come I know that the multiplicity is 2? Well, think about the term, the factor term is x minus 7 whole to the power 2, so you know that it is there twice. And that is even. So as soon as I know that that is even, I say that the graph touches the x-axis and bounces back. For the next problem, it's going to be a little bit of work for us, but remember, we're still talking about the same thing. So we actually need to factor it this time. The first thing that I have noticed that all three of these terms, they have x in common, so I can factor out the x and get x squared minus 6x plus 9 equal to 0. Then factor the x squared minus 6x plus 9. So you were looking for two terms that multiplies to 9 but adds up to negative 6. Clearly the terms are negative 3 and negative 3. So I go ahead and say that this is x times x squared minus 3x minus 3x plus 9, which is equal to 0. So I get x times x minus 3 when I factor out x from the first two terms. And then when I factor out negative 3 from the second pair of terms, I get negative 3 times x minus 3 again. So the group of terms x minus 3 is common in both of them. I will factor it out, and my factors are going to be x times x minus 3 times x minus 3, which you can write as x times x minus 3 to the power 2. The reason I write it this way is because it is going to help me understand the zeros. So now we're going to answer questions. Zeros for this polynomial is either x is equal to 0, that's the first one, or x minus 3 equal to 0, or you can say x minus 3 squared equal to 0, which is essentially saying x minus 3 equal to 0, and that says x is equal to 3. So zeros are 0, comma 3. And then the leftmost 0, well, the smaller one is 0, so the leftmost 0 is 0, and the multiplicity is 1, because it is with the power of 1, which is odd, so crosses. I'm not going to write the entire thing, but you remember what do I mean by when I say crosses. I said that the graph crosses the x-axis at this x-intercept. The rightmost 0, whereas, is going to be 3. But 3 is there twice, so multiplicity is even. and that means it touches the x-axis and then bounces back. So it touches the x-axis and bounces back. And maybe I should be a little more precise when I say touches or crosses. Remember, these are your real x-intercepts. So in the first example, when I did it, when I said the 0 is -3, and I said graph crosses the x-axis, it is crossing at -3, 0 at this point. And at 7, the graph touches and bounces back, so it is happening at 7, 0. In the second example, at 0, it is going to cross, so the crossing is happening at 0, 0. And at 3, it is going to touch and bounce back, so that is happening at 3, 0. All of them are x-intercepts. All right. In our next example, we will talk about a theorem which is called the intermediate value theorem. And in fact, we are talking about this thing about the polynomial function, but it is true for any continuous function where the graph is continuous. It doesn't even have to be smooth. If f be a polynomial function with real coefficients and f of a and f of b have opposite signs, then there exists at least one value c between a and b for which f of c is equal to 0. Equivalently, the equation f of x has at least one real solution. So how do you know, given a polynomial and given two numbers, whether there is a solution between these two numbers? Well, the easier answer is find the value of the polynomial function at these two given numbers. If they are of different sign, then you know that there is at least one real solution between the two given numbers. For example, our polynomial function is 4x to the power 4 minus 8x squared plus 2, and I'm wanting to know whether there is a real solution between -1 and 0. So on the number line, I'm thinking about -1 and 0, and I want to know what happens with f of -1 sign-wise. So f of -1 is 4 times -1 to the power 4 minus 8 times -1 squared plus 2. Then we simplify. So let me write it a little smaller because I want to use the number line to have a pictorial identification. So 4 times -1 to the power 4 minus 8 times -1 squared plus 2. So -1 to the power 4 is just +1. So this is 4. Similarly, the next one is -8 plus 2. 4 minus 8 is -4 plus 2 is -2. So at -1, the value of the function is -2. So say somewhere here. This is f of -1. Well, how about f of the other given point, which is 0, and between -1 and 0, I want to know whether there is a real solution. So what I get 4 times 0 to the power 4 minus 8 times 0 to the power 4 plus 2. Remember, the first two terms are simply 0. So it's 0 minus 0 plus 2, which is 2. And that is positive. So 2 is positive, whereas we have seen that -2 is negative. Positive 2 means I'm going to get the value of f of 2 over the x-axis. And you don't have to know how the polynomial function behaves, but it behaves continuously and smoothly before it reaches f of 2. Now see, I have at least one point where the graph has been crossing the x-axis, and remember this is a real 0 because that's the x-intercept. So I can say, yes, there is at least one solution. Yes, there is at least one real solution. So intermediate value theorem doesn't talk about complex solution. It is going to talk about real solutions. Now, I have given you one of those pictures, but you can also think about a graph which is like this. This is also a polynomial function, and see, in this situation you have 1, 2, 3, 4, 5, at least 5 real solutions, 5 real x-intercepts between -1 and 2. So intermediate value theorem doesn't tell you exactly how many solutions you're going to have. It just tells you you will have at least one real solution. Again, it talks about real solution. existence of them between two real numbers if the value of the function evaluated at these two given real numbers are of different signs. Use the leading coefficient test to determine the graph's end behavior. So as we can imagine, we're going to talk about the leading coefficient. So I can write the leading term to start with. That is the highest powered x term. So the coefficient, the leading coefficient is the coefficient of this term. And that is clearly 1. And remember, we are interested in the sign of the leading coefficient. It is positive. The degree of the polynomial is the other thing we need for the end behavior. And the degree of the polynomial is the highest power, which is 4. And that's even. We are interested in odd or even for the degree. So what we do? Even degree, positive leading coefficient is like x squared. So it goes up. So both ends go up. Or you can say as x goes to far right, y goes to infinity. As x goes to far left, y goes to infinity. Find the x-intercepts. So I need to know the zeros of this polynomial function. So we'll say x to the power 4 minus 4x squared equal to 0. And now what I need to do is factor. So factor out x squared because that is present in both terms and you get x squared minus 4. Then improvise a little bit. So now say x squared times x squared minus 2 squared, and I wanted to do it because 2 squared equal to 4, and that gives us the form of a squared minus b squared. So the sum of a plus b multiplied by the sum of a minus b. What do I mean by that? That means x squared times x plus 2 times x minus 2 is equal to 0 by factoring. So then the question asks me at which 0 does the graph of the function cross the x-axis or touch the x-axis and turns around. So the zeros are things that I'm going to first find out. So x squared equal to 0 will give you x equal to 0, and the multiplicity is 2 because of the power of the factor, and that is even. Okay. The other zeros are going to come from the factor x plus 2 equal to 0, which is going to give you x equal to negative 2. So clearly multiplicity is 1. That's odd. And the third and final 0 is x minus 2 equal to 0, which gives you x equal to positive 2. Again, the multiplicity is 1, which is odd. So I say crosses x-axis. This graph will cross the x-axis at odd multiplicity, which are negative 2, 0 and 2, 0. But the graph will touch and bounce back x-axis. So it will touch x-axis and bounce back at the point with even multiplicity, which is the solution 0, 0. That's it. Find the y-intercept by computing f of 0. So now we will say f of 0, and f of 0 is going to be, you just simply plug in 0 in your given function. So you get 0 to the power 4 minus 4 times 0 squared, which is 0. So the y-intercept as we write it is x equal to 0, comma y equal to whatever we found out, and we found it to be 0. So that is what we get. Is it odd, even, or neither? So remember, a function is going to be odd if it is symmetric about the origin. And what do I mean by that? Symmetric about the origin? I mean, if I change x to negative x, then the outputs are going to be the same value but negative of each other. So let's try to write it a little more precisely. If you change the input from positive to negative and then evaluate the output, then the output of these two will be same in value, but they will be negative of each other. So minus f of x is f of negative x. And one of the ways I remember this thing always is remembering the very fact that I can pull this minus out of the function. From the variable, it goes through the function and goes out. That's odd. Whereas a function is even if the graph of the function is symmetric about the y-axis. So if it is symmetric about y-axis. What do I mean by that? So similar situation, you change the input from positive to negative and find the outputs. If the outputs do not change, if they are equal to each other, even changing the input from positive to negative, then it is symmetric about the y-axis. Different x's, positive, negative, gives you the same height. So symmetry about y-axis. So that is even function. And if none of them happens, then it's neither. For our example, our fx is equal to x to the power 4 minus 4x squared. So we will find out f of negative x, which will be minus x to the power 4 minus 4 times negative x to the power 2. So remember, even power of negative numbers, just change it to a positive number, so the minus goes away and I get x to the power 4. Then minus 4 times the same thing, even power of negative number is positive. So what I found out, f of negative x is f of x. Changing the input from positive to negative did not change the outputs. I still have the same output, they're equal to each other. So this function is actually an even function or symmetry about the y-axis. All right. Our next example is asking us to determine the graph of the given function that we talked about. So remember where the information we found out. The first information that you found out about this function was it has solutions at 0, negative 2 and 2. So those are three x-intercepts. At negative 2, 0 you cross the x-axis. At 2, 0 you cross the x-axis. At 0, 0 you touch the x-axis and bounce back. And both ends of this polynomial function will go up. It will be symmetric about y-axis and it will cross the y-axis at 0, 0. So which one of them is going to satisfy all the information? So see what I have in the first one. Negative 2, 0 you are crossing the x-axis. 2, 0 you are crossing the x-axis. 0, 0 you are touching and bouncing back. Both ends are going up. Graph is pretty symmetric about the y-axis. And it is crossing the y-axis at 0, 0. So the very first one satisfies all the information and is my correct choice. Alrighty. So then we have a long example where we are given with bunch of information and the question asks you to which of these following formulas could be a polynomial with all of this information true. So see what are the information. The first one says the solutions are negative 9, negative 3 and 5. So what I do, I look through my list and see which one of them has the same set of solutions. So this one, the solution is negative 9, negative 3 and positive 5. Negative 9, negative 3, positive 5. This is positive 9. So I immediately strike it out. Let me actually use the red color and I see that number B also has 1/4 solution. So if you look at B one more time, it has negative 9, negative 3 and 5, but it also has x equal to 0. So the solutions are 0, negative 9, negative 3 and positive 5, which is not our situation. So we'll strike it out, cannot be my situation. The next one, as we talked about, the solutions are 9, 3 and negative 5. Not our solution, gone. Again, let's just use the red to strike it out. If I look at the next example, I have negative 9, negative 3 and positive 5. So that is good. So I'm going to keep this. The next equation is negative 9, negative 3, positive 5. Negative 9, negative 3, positive 5. Negative 9, negative 3, negative, positive 5. All of them are good. What next? So the next information is It has y-intercept at y equal to 3. So if I put x equal to 0, then y must be 3. So I will do one by one. Say for example the first one. Put x equal to 0. So your y is going to be negative 3 over 135 times 9 times 3 times negative 5. So if I simplify this thing and use my calculator to do it, then I will see 3 times 9 times 3 times 5, and that's a negative 5. That's the top, and the bottom is 135. So if you remember how much was the bottom, it was 135, and then there is a minus in front, so I can put that minus with this bottom. I will get 3, and that's exactly what I needed. So what does that tell me? That this one still now is a competitor. Let's go to D, the fourth one, and do the same thing. So you have negative 3 over 405 times 9 times negative 3. Actually, there should be, if I put x equal to 0, I get 3. So 3 squared times negative 5. So let's work it out. Again, I'm using my calculator and I'm doing the top. So 3 times 9 times 3 times 3, that's the 3 squared, times 5, which is negative. That's the top. And I divide by 405, but do not forget the minus in front. I'm just using it in the bottom. It's still 3. So that's good. We'll go to the next one and we will say y is equal to. So the first one and the second one, both actually this is the third one, the fourth one, but that's the second one that we wanted to check. They're both good. So the next one is y equal to negative 3 over 3645, and I have 9 times 3 to the power 4, so negative 5. Let's multiply and see how much we get on this. You can use this minus in front to the top as well. So instead of calling it 3, I can call it a negative 3 and then multiply 9. And then remember, I'm multiplying 3 to the power 4. And finally, we're multiplying negative 5. So that is the top. And the bottom this time is just going to be 3645. So divide by 3645. I still get 3. So this is also a nice competitor. Next one. You have 3 over 675. So y is equal to 3 over 675 times, I'm putting x equal to 0, so I get 9 times 3 times, this time you have negative 5 to the power 2. So let's find it out. So I can actually forget about the minus because the minus is squared, so I will eventually get a positive answer. So start with 3 times 9 times 3 times 5 squared is 25. And then I divide that by 675. I still get 3. So this is also nice, y-intercept wise. The last one in my list is minus 3 over 1215 times 9 squared times 3 times negative 5. So as I said earlier, you can use the minus in front of the expression to the top or the bottom, does not matter. Let's use it with the top. So instead of saying 3, I call it negative 3 times 9 squared, which is 81, but let's just multiply the way it is, times 3 times negative 5. Divide by 1215, I still get 3. So this information actually did not help me a lot, as all of the remaining 5 are nice expressions for the y-intercept. What else we have? We have, as x goes to positive and negative infinity, y goes to negative infinity. That is the long run behavior. So as x goes to infinity, y goes to negative infinity. As x goes to negative infinity, y still goes to negative infinity. So both end goes down, which is even degree. So the polynomial must have even degree and negative leading coefficient. So let's see that situation. So when I look at the first one, I see that the leading coefficient is negative. The third one, leading coefficient is negative. The fourth one, leading coefficient is negative. F is where the leading coefficient is positive. Cannot be your situation, so strike it out. Then we're going to talk about the even degree. How much is the degree of the first one? Well, see, the degree is 1 plus 1 plus 1, so the degree is 3. So that's odd, so cannot be my situation. So this is odd degree and can be my situation, so I have to strike this one out as well. So now we have only 3 competitors. Okay, this one, the degrees are 1 plus 2 plus 1, which is 4, so that's good. The next one is 1 plus 4 plus 1, so that is 6, good. 2 plus 1 plus 1, so 4, even degrees, so all of them are good choices. So with the given information, I would say the information are true for all of D, E, and G. And we have answered the question accordingly. So the next problem is simply solving a polynomial equation. And this equation, if you're careful, then it looks like a quadratic equation with the exception of the power being 4. So what you can do, you can solve it as a quadratic equation. So it always helped me to write it as x squared, that's x to the power 4 term, minus 5x squared plus 6. Then remember we multiply a and c and both of them are 1. So I wanted two numbers that multiplies to 6 and adds up to negative 5. Clearly they are negative 2 and negative 3. So write it as x squared minus 2x squared minus 3x squared plus 6 and start factoring by grouping. So the equation, so it is equal to 0. The first two terms you can factor out x squared, get x squared minus 2. From the second pair of terms you can factor out negative 3, still get x squared minus 2. So now I can factor out the group of terms x squared minus 2 and I will get x squared minus 3 as the other factor. Product 0 rule is either of these factors will be treated as 0. So x squared minus 2 is equal to 0, which means x squared equal to 2. Use the square root rule. Take the square roots on both sides. Do not forget the absolute value of x equal to square root of 2, which will give you two solutions, square root of 2 and negative square root of 2. The other factor is x squared minus 3 equal to 0. So x squared is positive 3. I take the square roots on both sides. Absolute value of x is square root of 3. I get twofold solution, square root of 3, negative square root of 3. So if I was asked to list all these solutions as in a set, I will say the solution set is negative square root of 3, the leftmost 0, negative square root of 2, positive square root of 2, positive square root of 3. So that would answer this question of ours. Okay, we will solve a couple more polynomial function. So this one is find all the zeros of the function fx equal to x squared plus 2x minus 10 times x cubed plus 4x minus 12x. So what you do first, you write it as x squared plus 2x minus 10 times x cubed plus 4x squared minus 12x equal to 0. So either x squared plus 2x minus 10 equal to 0. Now this is a quadratic equation, so I know how to solve it. So use the quadratic formula. Remember a is 1, b is equal to 2, c is equal to 10. So quadratic formula says x equal to negative b plus or minus square root of b squared minus 4 times a times c over 2 times a. So it says that do not enter decimal approximation. So our answer must be in standard form. So what I get x equal to minus 2 plus or minus. Under the square root, I will have 4 minus 40 over 2, which is minus 2 plus or minus square root of negative 36. So I get complex answers, which is equal to negative 2. So let me write it one more time. Negative 2 plus or minus
Square root of 36 is 6. The negative will give me the I over 2. And finally, I can write it as negative 2 plus or minus 6i, but both of them I divide by 2. Distribution of the division. So I get negative 1 plus 6i or negative 1 minus 6i as the two solutions from only the first factor. The second one is x cubed minus 4x squared minus 12x equal to 0. As usual, you can factor out the x because it is present in all of them and write it as x times x squared minus 4x minus 12. And then you factor the inside. So I will get two numbers that multiplies to negative 12 but adds to negative 4. And these are negative 6 and positive 2. So x minus 6 and x plus 2. And that gives us three more solutions. So either x equal to 0 or x equal to 6 or x equal to negative 2. So I have total 5 solutions to the polynomial equation. 2 of them are complex numbers, so they are not x-intercepts. 3 of them are real numbers, so these are your x-intercepts, 0, 6 and negative 2. Find all real number solutions for the following equation. So it's a fifth degree equation, but if I look carefully, I see that x minus 1 to the power 3 is common in both. So I factor this group out and I get x minus 1 squared minus 2 equal to 0. So either x minus 1 to the power 3 is equal to 0, which means x minus 1 equal to 0, which means x equal to 1, and this is a multiplicity 3, 0. Or the other factor is x minus 1 squared minus 2 equal to 0. So add 2 on both sides, you get x minus 1 squared equal to 2. Take the square roots on both sides. So absolute value of x minus 1 is equal to square root of 2. I get two solutions out of this. Either x minus 1 equal to square root of 2, so x is equal to square root of 2 plus 1, or x minus 1 equal to negative square root of 2, so x equal to 1 minus square root of 2. So I still get 5 solutions, but 3 of them are the same number 1. So multiplicity of that solution is 3. And all of them are real numbers, so I get 5 x-intercepts, even though the graph is going to cross the x-intercept 1 because of the odd multiplicity. And the other 2 x-intercepts are going to be square root of 2 plus 1 comma 0 and 1 minus square root of 2 comma 0. Again, odd multiplicity, both of them are 1, so graph will cross the x-axis at these points. Next equation is 2x minus 5 times x minus 2 squared equal to 0. And it is actually pretty simple. You just set 2x minus 5 equal to 0. So x is equal to 5 over 2. Or you set x minus 2 squared equal to 0. So x minus 2 equal to 0, so x equal to 2. Just remember to think that is a multiplicity of 2 because the 0 is there twice. So at 2, the graph will not cross the x-axis. It touches and bounces back, whereas at 5 over 2 comma 0, the graph will cross the x-axis. My next problem is solving for real numbers, zeros. 1 times x to the power 6 minus 2x squared equal to 0. So what I do? Well, x squared is common, factor it out. You get x to the power 4 minus 2 equal to 0. So either x squared is equal to 0, which means x is equal to 0, but multiplicity again is more than 1, is 2. The next solution is x to the power 4 minus 2 equal to 0. So I can say x to the power 4 is equal to 2. Take the square roots. So I get absolute value of x squared is equal to square root of 2. But I want to solve it for x. Remember one thing, x squared is always greater or equal to 0. Think about the graph. It's a non-negative quantity all the time. So I can remove the absolute value. That means x squared is equal to square root of 2. Take the square root one more time. So you get absolute value of x is square root of 2, which is x equal to square root of square root of 2 or x equal to negative square root of 2. And these are the solutions to this polynomial equation. So what I say that there are 4 real solutions. One of them is repeated, and that is x equal to 0. And the other 2 real solutions are negative square root of 2. 0 is twice, and then square root of 2. The other 2, because it is a 6-degree polynomial, I should have 6 solutions, only 4 of them are real, so the other 2 are complex numbers. But we wanted to find only the real solutions, so we are good. So this is precisely our lecture note for the understanding of the graph of the polynomial function and solutions. In our next class, we will talk about factor and remainder theorem, long division, and trying to find out other ways to talk and find solutions of a polynomial function.